Okay, let's come back to part B, concept 21.2. The second law of thermodynamics, during any energy transfer, some is dispersed and becomes unusable. Typically things like heat, right? Thus, available energy will decrease at each trophic level. When we put animals in, it gets more complicated than just like energy transfer via a physical mechanism. And the trophic pyramid portrays the relative amounts of energy or biomass in each trophic level. And energy on an annual scale and biomass are different. And we'll look at that in the next two figures, which I think are very important. And that terrestrial ecosystems' energy and biomass pyramids are similar because biomass is closely associated with energy production. So what we're looking at here is, let's just look at the mass space. We have a lot of mass of primary producers. 10 times less, it's not exact, but an order of magnitude less biomass of herbivores than primary carnivores and secondary carnivores. So as we go up each trophic level, the biomass for that trophic level gets markedly smaller. Now, energy, typically we would think about energy on an annual scale. So how much energy is created via primary producers in a year? How much of that energy is transferred to herbivores, primary carnivores, and secondary carnivores? And so generally the same shape as we get into the primary and secondary carnivores. It gets much thinner, but generally this idea of a pyramid where you have a lot of biomass for your primary producers and then subsequently lower as you get up each trophic level. Now that changes in, this is aquatic, the same is true for marine, and so we can use aquatic as a proxy for marine, and aquatic, to me aquatic means freshwater, but nonetheless, we can look at this in aquatic systems compared to terrestrial. Now let's start with biomass. You have a small amount of biomass in your primary producers, more biomass in your herbivores, more biomass in your primary carnivores, and more biomass in your secondary carnivores. Now that doesn't make sense, right? Like, how can there be more herbivores than there are primary producers, right? It's like having a larger biomass of cows than you have of grass. And the difference here really is turnover rate. So if a phytoplankton lives for a week, 2 weeks, a tree can live for 2,000 years. So it has this massive amount of biomass, but it's not turning over. It's not being consumed relatively quickly. It's growing biomass, growing biomass. Even in grasses, you can think that a good portion of the biomass of the grass is below ground. What's available for most herbivores is the above ground portion of the grass. And that could live for decades, right? Where if you're a phytoplankton, your overall energy production for the year, if we look at all of aquatic systems, is pretty similar to that of all of terrestrial systems, meaning that the primary production, if you want to go net primary productivity, for example, is the same between aquatic systems and terrestrial, but the biomass of which is needed to achieve that net primary productivity is much less because it's turning over more rapidly. And so one thing I'm trying to think of a good analogy here. When we're trying to look at food production, and in my work, food production is things like clams and intertidal foods. We need to know both biomass, what's the standing stock of things you can eat, but also what's the productivity of that system. And so you can have two systems, imagine two beaches. One is full of clams, and the other one has very few clams. And so if we do the biomass, we'll say, okay, beach A has a lot of clams and beach B has very few clams. So beach A is better, right? But what if beach A has a lot of clams, but they're not really growing? They're there, they're kind of barely hanging on, but they're not really growing, where beach B has fewer clams, but they're growing much more quickly. And so if we want to look at the amount of biomass increase over the year, it's effectively what they're calling energy here. So that's the amount of biomass that we could harvest every year off that beach and not impact the overall longevity of that population. And so if beach B has fewer clams, but they're growing much, much quicker, it can actually generate more food compared to beach A, which has more clams, but they're not growing. They're just kind of barely hanging on. And so that's that difference here between biomass and energy. And so it's interesting to look at the differences between the two. And so here in aquatic systems, you have a small biomass that's doing a lot of primary productivity, generating, fixing a lot of energy, that's then being consumed by a greater mass of herbivores than they are. In this case, zooplankton, copepods, whatever it might be. And so here you have a copepod that lives for a year, but the thing it's eating only lives for a few days. And so there's a relatively small biomass of them, but they're really productive. And so that's feeding the levels up. And then going on to primary carnivores, in this case would be things like fish that eat zooplankton, herring, anchovy, etc. And then secondary carnivores, salmon. Again, in aquatic systems, we can have higher trophic levels. It's more easy to have higher trophic levels than it is in terrestrial systems. And so here we could have a phytoplankton being eaten by a zooplankton that's being eaten by a herring that's being eaten by a salmon. So that gets to our secondary carnivore. That's our fourth trophic level. That salmon could be eaten by a sea lion, and we'll talk about that in a second. And then that sea lion could be eaten by a shark or an orca whale. So now we've got 6 steps to our trophic level. So we've got primary producers, herbivores, primary consumers. Primary consumers here were herring. Primary consumers are herring. Sorry, primary carnivores. I'm getting my words mixed up here. Primary producers, phytoplankton. Herbivores, zooplankton. Herring are primary carnivores. Salmon are secondary carnivores. Sea lion are third level carnivore. And then a shark or an orca whale, which would be our fourth level, our fourth level carnivore. And so it's and I also think about the shape of the graph too. On the terrestrial, it gets smaller and smaller and smaller. So if you had a carnivore, a third level carnivore, it has a really small biomass it can be eating, and that's an issue because of the distribution of food and then the amount of energy required to find that prey. It would be quite difficult. Where in the marine environment, you've got a large biomass of secondary carnivores. There's a huge biomass of, let's say, salmon. Most fish that we eat are piscivorous, meaning they're eating other fish, and those fish are eating zooplankton, and those zooplankton are eating phytoplankton. So there's a larger biomass for them to draw on, as well as it's easier to move. I mean, it's not easier to move through the aquatic realm is like arguable, but they're moving through a more constant environment as opposed to having to cross mountain ranges, etc. So that's part of the reason why we can have more higher level carnivores in marine systems compared to terrestrial. And then we can look at the energy derived by those. And so here's the amount of energy contained that goes into each of those. And so you can have the differences in biomass and then that energy transfer. So even though there's a large biomass in things like primary and secondary carnivores, they represent a relatively small amount of the overall energy in that system, because so much of that energy is at the lower levels that despite a low biomass, it's turning over quite a lot. So this is called an inverted pyramid. who was the first? I think it goes back to Odin. Odin in the 40s had written about this, so it's been around for a while. The inverted biomass pyramids are more common where production is the lowest, such as nutrient-poor regions of the open ocean. Phytoplankton turnover is higher, associated with higher growth rate and shorter lifespan compared to phytoplankton in more nutrient-rich waters. So you're more likely to see this in the open ocean compared to coastal oceans that have a fair amount of nutrients via upwelling. And so here we can look at 3 different aquatic and marine systems: open ocean, coastal oceans, and lakes. If the biomass ratio of heterotrophs over autotrophs is greater than 1, we would have an inverted pyramid, meaning if you add up the mass of this, divide it by the mass of this, that answer is going to be greater than 1. Where if we add up the mass of this, divide it by the mass of primary producers, that's going to be less than 1. And so this is the inflection point where we go from a regular pyramid to an inverted pyramid. Here's a log autotroph biomass and then this ratio. And so what you can do is follow a single system, like let's look at lakes. If there's a low autotroph biomass, then you're more likely to have an inverted pyramid. If there's a high autotroph biomass, i.e. plankton, you're more likely to have a regular pyramid. And so it's most pronounced in the ocean, where the majority of the open ocean, the majority of the distribution is on the inverted pyramid scale. So within a system, as it goes from either oligotrophic, meaning low amounts of nutrients, to eutrophic, having lots of amounts of nutrients, it'll move along this gradation of inverted to regular pyramids. Factors affecting energy flow: the amount of net primary productivity at the base of the food web, proportion of each trophic level consumed by the one above it, the nutrient content of autotrophs, detritus, and prey, and the efficiency of energy transfers. And so we're going to walk through those. Herbivores on land consume a much lower proportion of autotroph biomass, about 13%, than herbivores in aquatic systems, about 35%. Meaning of the biomass of plants, autotrophs on land, about 13% of those get consumed on an annual basis. In herbivores, in aquatic systems, zooplankton, etc., consume about 35% of the autotrophs, in this case primarily plankton. Although there's kelp and other things like that, but mostly it's plankton on a mass scale. The positive relationship between net primary productivity and the amount of biomass consumed by herbivores suggests that herbivore production is limited by the amount of food available. Later in this chapter, we'll get into bottom up versus top down, but we'll kind of break that down some more. So here, this is a log-log plot. Net primary productivity and consumption by heterotrophs. This is not a percentage. This is a grams carbon per meter squared per year. Same thing down here, grams carbon per meter squared per year. So you could do a ratio of these, but this is just the raw data. The way to think about this is to say, okay, if I'm in a system that has 100 grams of carbon, of net primary productivity, 100 grams of carbon per meter squared per year, so meter squared per year, if that generates 100 grams of carbon, and I'm in a terrestrial system, I go over here. This is a log plot, so it's kind of hard to estimate, but it's probably a log plot that's got to be greater than 10. 20 or 30 grams of carbon are consumed. So if I have 100 grams of carbon fixed through net primary productivity, some amount, 20, 30 grams of that is going to be consumed by heterotrophs. Actually, if we use the ratio from above, it was 13 and 35. So that's for a terrestrial system. If we move to an aquatic system, the same amount of net primary productivity, 100 grams of carbon per meter squared per year, and we move up here and come across, yeah, because actually log would be spread out and then start getting tighter up here. Yeah, maybe. So some higher number, 35, 40, 50%, or 50 grams would be consumed. So that's the best way of thinking about it, is move along the X and then see how being in either aquatic or a terrestrial system impacts the Y, is really what we're trying to look at. So why don't terrestrial herbivores consume more of the available biomass, right? You're only eating 13%. What's going on? You should really learn from the ocean. There are several hypotheses. One is that herbivores are constrained by predators and never reach carrying capacity. We'll come back to that. That's top down. Predator removal experiments support this hypothesis in some ecosystems. And so, meaning the bunnies would eat all of the grass, but the lynx get them. Or autotrophs have defenses against herbivory, such as secondary compounds, spines, etc. Very much true. Plants spend a good amount of their energy on secondary compounds and defenses. Think about plants in resource-poor environments. There's a reason why cacti have spines, right? And most plants up here don't in more temperate areas. So resources are more limited in those desert environments, so they need to invest more energy into defense because there's not so many tasty plants to eat. And unicellular algae generally lack chemical defenses, meaning phytoplankton generally lack chemical and structural defenses. There's examples of phytoplankton that produce toxins. The question of how that impacts their likelihood of being consumed are probably variable, and it's a minority of phytoplankton that do that. Phytoplankton are more nutritious for herbivores than terrestrial plants, which have structural compounds in them, wood, cellulose, things like this. So you think about a panda eating bamboo. It's not really the most nutritious thing, where phytoplankton are just full of delicious nutrients and easy to digest. So the ratio of carbon to nutrients, such as nitrogen and phosphorus, are an indicator of food quality. Freshwater phytoplankton have a carbon to nutrient ratios closer to that of their herbivores than terrestrial plants do, meaning that they're more nutrient rich. That when you look at the elemental ratio of a phytoplankton, the carbon, nitrogen, and phosphorus, it's much more similar to that of their predators, zooplankton, compared to looking at the distribution of carbon, nitrogen, and phosphorus in a bamboo compared to a panda. So, meaning they're more nutritious. They can digest the entire thing. And there's trophic efficiency, the amount of energy at one trophic level divided by the amount of energy at the next lowest level. So how much energy is lost through each trophic level, and that can be defined as three different parts. Consumption efficiency, the proportion of the available energy that's ingested. This is generally higher in aquatic systems than it is in terrestrial systems, and higher in carnivores. Okay, let's go back to a zooplankton eating a phytoplankton. It's all easy to digest. They're going to digest most of that phytoplankton. A panda eating bamboo, they eat 20 to 40 pounds of bamboo a day. Most of that's passing through the other side undigested, right? All that cellulose and stringy stuff. And so they have a relatively low amount of the energy is ingested. A lot of it is passing through. Okay, yeah, that could be. And then carnivores, meats more nutrient dense. I want to come back to this one, I think. Let's see. Consume. Yeah, let's come back to that. Let me move that down here. Yeah, I'll come back. Okay. There's assimilation efficiency, the proportion of ingested food that's assimilated that depends on the food quality and consumer physiology. Food quality of plants and detritus is low because of complex compounds such as cellulose, ligands, humic acids. which are not easily digested, and low concentrations of N and P. So maybe that's a better example for the panda and bamboo than what I said before, which is consumption efficiency. So animals have a carbon and nutrient ratio similar to the animals consuming them. So carnivores, animals eating animals, we have generally the same ratio of nitrogen, carbon, nitrogen, and phosphorus. Assimilation efficiency of herbivores and detritivores are about 20 to 50%, and carnivores are about 80%, meaning when you eat a steak, you assimilate about 80% of energy. Compared to if you eat some celery, you're not going to assimilate as much of that energy. Endotherms digest food more completely than ectotherms and thus have higher assimilation efficiencies. And we'll come back to some of the difference between endotherms and ectotherms. Some herbivores have mutualistic symbionts that help them digest, i.e. the ruminants, cattle, deer, camels. Have the ruminate things, the modified foregut with bacteria and protists that help break down cellulose, and have higher assimilation efficiencies than other herbivores. So they've adapted to being able to extract as much energy out of what they consume, i.e. the assimilation efficiency compared to herbivores without those adaptations. And there's production efficiency, the proportion of food, of assimilated food that goes into new consumer biomass, strongly related to the thermal physiology and size of the consumers. Ectotherms allocate more energy to heat production and have less for growth and reproduction than, did I say, yeah, I think I said endotherms compared to ectotherms, meaning endotherms were generating heat, which is burning energy, and so that's when you have so much energy and you've got more places to put it, you're going to have less for other things. And so if we're putting a lot of energy into generating heat, we're burning off that energy, which means we have less energy left for growth and reproduction. We'll go back to this here. So body size affects heat loss in endotherms. As surface to body size increases, the surface area to volume decreases. So a small endotherm, e.g. a shrew, loses a greater proportion of its heat across its body surface than a large endotherm, such as a grizzly bear, which will have a lower production efficiency. Meaning that it's easier for a large animal to stay warm than it is for a small animal, because a large animal has more internal mass, more volume, compared to the amount of surface area, where a small animal has more surface area for their given volume of mass. Okay, so I want to jump back because I misspoke a bit, and the graph will explain this better, but consumption efficiency is the proportion of food consumed relative to the amount of food available. So kind of back to the terrestrial and aquatic difference, where in aquatic systems there's a higher consumption efficiency, more things are being consumed when we go from the amount of net primary productivity to how much makes it to the next level. The amount that you're eating is consumption efficiency. So think of it as in the trophic layers, if you're on the second layer, you're an herbivore, how much of the available primary producers or autotrophs are you consuming? Same thing if you're a carnivore, the first level carnivore, how much of the herbivores are you eating? We'll walk through it in the graph again. And so where assimilation efficiency, the panda example is probably a good one to think about. So we can put that in a conceptual diagram. And so think about the overall net primary productivity. The consumption efficiency is this part. So we have all of the net primary productivity. Consumption efficiency is how big is this part of the wedge. And so if we had a high consumption efficiency, we could be consuming most of the net primary productivity. Now, so we consume some portion of the amount of available energy from the level below us, in this case, our autotrophs or primary producers. That food is consumed. Some amount of that energy is assimilated, is made available to the organism, and some amount passes through urine and feces. Now that again depends on the quality of the food. If you're eating celery versus hamburgers, more of that celery is going to pass through you, and you're not going to be able to utilize the nutrients within that, the cellulose, etc. Compared to if you're eating a hamburger, or just the meat, a steak, we process meat very efficiently. I'm not getting into a debate about herbivores versus carnivores. I'm just saying that that's true. You can look at other animals as well. And then respiration is the amount that we're losing through respiration. And so this could be, part of that's related to being an endotherm or an ectotherm. As an endotherm, we're burning more energy to keep up heat. So we're going to have a higher respiration per unit mass. And then what's left over winds up going up into biomass. And that biomass is then what leads to the biomass of your, in this case, an herbivore, right? So you could think of it this way, as the mass of herbivores is equal to the consumption efficiency, how much of the primary production is being consumed by herbivores, how efficient the herbivores are about extracting the energy from that food, how much they lose through respiration, and then how efficiently they're able to take that leftover energy and convert it into biomass. So those are the key components we need to understand if we want to figure out, hey, this field has a primary productivity of X. How many pounds of cows can I grow on it every year? We need to know, well, how much of the grass will the cows eat? How efficient are they extracting those calories? How much of those calories are lost through things like respiration? And then how efficiently are they turning the leftover calories into biomass? I want to jump back to the small and large endotherm thing. And I talked about Bergman's rule in chapter 4, but I want to bring it up again because I like Bergman's rule. Okay, sorry, I was looking at some other exam type questions I wrote down around the inverted pyramid. So Bergman's rule is basically saying that as you move up in latitude, as you get to more polar regions where the climate tends to be colder, the average biomass of a given organism gets larger, and that has to do with the biomass, the volume, the surface area to volume ratio, which as you get larger, you have more volume per your surface area. And so it's more efficient to stay warm if you're big because you've got less skin, surface area, the heat's being pulled out of to compared to if you're smaller. And so this is evidenced by the average size of a moose. In higher latitudes where presumably it's colder, the moose are larger compared to lower latitude areas where they tend to be smaller. And again, the example I gave in chapter 4, which I'm bringing up oddly again just before the final, is also looking at white-tailed deer. And this is a distribution of the subspecies of white-tailed deer. And these deer down here are frequently called Coues deer. They're quite small. They're even smaller than our island black-tailed deer. So, looking at a 40 to 60-pound animal. Where if you're up here, and like Alberta's famous for having these giant white-tailed deer, if you want a 300 plus pound white-tailed deer, that's where you have to go. And it's related to that distribution of heat loss versus body size, where if you're a Coues deer in Mexico in the Sonoran Desert, you probably want to actually lose heat, right? Because it's warm. If you're in a colder climate where it's, you're walking around in snow for 6 months out of the year, you're going to want to retain that heat. So you're going to want to be larger. And so that's one way of thinking about this as it relates to body size and generally loss of heat. Let's see what we're doing. Oh, good. We're almost. We're getting there. Okay. So change in food quality or quantity impacts trophic efficiency and can determine consumer population size. Now I'm going to tell a quick story here about Steller sea lions. Steller sea lions have seen a decline in Alaska of about 80% over the past 25 years. There's also been some observations of smaller size and decreased birth rates, suggesting food quality and quantity might be a problem. So here's a graph showing the number of Steller sea lions from 1960 through 2000 showing lots, few acute stellars on a rock. And it's been recorded that their diet has changed. And so if we go back and look at 1976 to 78, they're having a relatively smaller proportion of cod, agadoids, mostly hake, or pollock actually in this area, salmon, and then a ton of small schooling fish, herring, capelin, oolacon, sand lance, little tiny fatty fish. They eat a bunch of those. And then no cephalopods or flatfish. In more recent years, the early 90s, big increase in the number of hake, consumed pollock primarily, salmon, not a big change, big reduction in the amount of schooling fish, herring, etc. And so this has been put together to say, okay, there's a change in trophic food, of like quality of food available, where a hake or a pollock is a fillet of fish, mick fish or whatever they are, fish and sticks, just like general, like non-offensive, bland white fish, and so it's very low in oil content compared to something like a herring, that is, or oolacons, which are very high in fat content, so they're very nutritious. And so this was one of the reasons they said, okay, well, there's like a big change in their diet, so that's impacting survivorship, size, reproduction. All of that undoubtedly is an impact. And also the decline in stellars may be related to trophic interactions. Some thought around the 20th century whale hunting may have forced whales' predators, killer whales, to switch prey, including sea lions, meaning that killer whales might have less other whales to eat, so they're eating more sea lions. What we're looking at, and we'll talk about in the next section, is top-down versus bottom-up. Which one's more important? Is it bottom-up, bad food? Is it top-down, things are eating me? Let me see if I have this up as my top one. I think I did. Oh, no. I'm reviewing the IRB standards. This is a report. Let me show it here. You can download this for free. It's kind of funny when you go to the website. They want you to pay $75 for a physical copy, $50 for an e-copy, or you can download the PDF for free. I'm like, well, what's an e-book if I can download the PDF for free? It kept saying this, you can download this for free, and I kept looking at it saying, I'm not paying $75 for this document. But, sorry, I took notes on what pages to look at here. But this is a report that was done by the National Research Council looking at these impacts on stellars and trying to kind of sort it out, including a good group of co-authors here. And so I want to just look at a few of their findings. So yeah, Bob Payne was the chair from the Estes. So Payne is the sea star guy, the keystone species, Estes, killer whale, otter, urchin stuff. Good. Okay, so I got page 4 is what I want to look at first. Acknowledgements, blah, blah, blah. Dun, dun, dun. I don't know. I'm not going to bore you with this, but I think it's important to be able to have differing hypotheses on an observed phenomenon. Let's see here. Try to see here. Okay, so they came up with 2 different hypotheses to explain this reduction in stellar sea lions. The first one are bottom-up hypotheses, meaning there's something bottom-up, meaning the things I eat are impacting me. And so they had a few bottom-up hypotheses. One is that large-scale fishery removals have reduced the availability or quality of prey species. The climate shift in the late 70s, which is confounding those earlier data, when the PDO switched. The climate regime shift in the late 70s changed the abundance of prey species. Disease, non-lethal diseases, is impacting the foraging efficiency of sea lions. Or pollutants concentrated in the food web of contaminated fish eaten by sea lions, possibly reducing their fecundity or increasing mortality. So all of those are, and it's in the answer to something like this isn't like, oh, it's point number 3 and that's it. They're arguably cumulative in impacts, but I think it's worth thinking about that. So for bottom up in review, it's fishing has changed prey, regime shift, diseases, pollutants. The second category, and we'll talk more about, why are you not listening to me? We'll talk more about bottom up versus top down in the next section, but I want you to know this. That top down hypotheses, these are things that could be eating the sea lions. So you could think of it, if you are an herbivore, I know they're not herbivores, but if you're an herbivore, you're eating things down, you're eating, algae or grass, and then things are coming from the top and eating you, bottom up, top down. Or if you look at it in the trophic levels, is it the trophic level above you or the trophic level below you that's having the biggest impact? So in this case, under top-down hypotheses that explain this reduction of stellar sea lions, could be predators such as killer whales, possibly sharks, have switched their prey preference to sea lions. Could be the incidental takes of sea lion capture or entanglement in fishing gear, result in expansion of commercial fisheries. So as we're fishing more, we're going to incidentally get more sea lions tangled up. It could be the take of sea lions in subsistence harvest were higher than estimated. There are a couple points of evidence where when we know like how many sea lions are taken for subsistence, but the capture efficiency is not always known, and so they're if only half of them are landed, and so they say, okay, this group caught 10 sea lions, but maybe the take was actually 20 and they lost half of them, that kind of thing. Shooting of sea lions that were underestimated in the past and present, we're going to talk a lot about that one. Pollution or disease, increased mortality, independent of effects of nutrients. So here they're saying, e.g., the introduction of contagious pathogen could decimate a population and give some appearance as an efficient predator. So here they're including diseases as a top-down effect if it's not impacting their forageability. And some of what I'm going to talk about also comes from Andy Rosenberg, who was at NOAA for a long time, who spent some time with us when I was in grad school. So, sorry. Let me go back to that. Sorry for the scrolling. I want you to hear these again. So under our top-down, predators, killer whales, entanglement in fisheries, subsistence harvest, shooting of sea lions, pollution or disease that's causing mortality independent of the effects of nutrition. So you've got 5 top-down possibilities. There's a couple sections I want to look at here. It's page 133 and 135 if you ever want to follow along at home. It's a really good report. I admittedly have not read the entire thing. But anyway, Andy talked about this when I was in grad school, saying that it's pretty well known that it was acute lead poisoning, meaning people shooting sea lions, was a big decline. And by that I mean it's not subsistence harvesters, it's people shooting sea lions for perceived interactions with fisheries. So the shooting of stellar sea lions was legal prior to the Marine Mammal Protection Act of 1972. However, passage of the act, fishermen were allowed to continue to shoot sea lions that were destroying their gear or causing a threat to human safety. And so that interpretation of that is arguably vague. And it was not until 1990 when the species was listed as threatened under the Endangered Species Act that discharge of firearms near stellar sea lions was fully prohibited. And so it wasn't until 1990 it was actually put into law or made illegal. There are a few recent cases of people being charged for shooting stellar sea lions, and especially with the Bristol Bay fishery and others. Crabbers apparently have a real bone to pick with stellars. There used to be a bounty program for stellars. The same thing was actually true here in the state of Washington. When my grandfather was a boy growing up on the coast, it was like $2 a snout for seals or sea lions. So let's look at page 130. What I got, 133. Long history of fishermen shooting sea lions, 30s and 50s. Some argument about how much that was an issue and how long it went on. There are limited data. There's actually this cool, I think it's 135 is a cool graph I want to look at. So it's the sort of thing that like it happens, most people know about it, but it hasn't been really that well documented. When I've been up fishing in Alaska, this is a while ago, it's been probably 15 years or more. The captain we went out with like fully admitted to shooting sea lions, and this would have been the 2000s. Particularly when he's out winter trolling for king salmon. So he's out on his boat by himself, trolling around all day for salmon, and you might catch 2 or 3. At that time of year, the price paid to fishermen is called the ex-vessel price, is probably $15 a pound, and you catch a 20-pound king salmon, and you might only catch, if you're lucky, 3 a day. And a stellar comes up and bites it off your hook. His response is to reach for the rifle and dispatch the sea lion. And he freely admitted that. It wasn't like a hushed secret. The question is how much of that's happening and can we quantify that? Apparently there's a big impact with crab for stellars. And so this is in the 60s and the 70s. Stellars were shot for crab bait. So they'd shoot a stellar, chop it up, and use it for crab bait, as well as the perceptions that stellars would attack the buoys and then mess with the crab traps as well. So they would also interfere in the fishery. And anecdotal mortality. Okay, I just want to look at this box here, box 6.3. There's a couple of good ones here. Recently, a Russian Orthodox priest who worked for years in the Kodiak, on Kodiak Island, thought there was no mystery at all to the continuing decline of stellar sea lions. During confession, he often heard fishermen talk about shooting sea lions. It's just like, not the like shooting part, but it's just like that's just a crazy source of information. An Orthodox priest. Oh yeah, during confession they tell me all about it. The Alaskan Sea Life Center and Stewart had planned a stellar display, but they thought that they would be shot if they were visible from the street. A fisher from southeastern Alaska claims she knew at least 25 fishermen who shot virtually all stellar sea lions on site. Let's see, a committee member on Sport Fishing Association in 2002 met with a fisherman who stated he had excellent fishing season, but most of his fish are being eaten by stellar sea lions. He was disgruntled. He did not have seal bombs. Seal bombs are like M80s. These are around here too. Yeah, some experience in the 70s of shooting all the stellars they see. So what I want you to know, and it's not is that there are multiple hypotheses to one phenomenon. In this case, sorry, let's go back to page 4 and I can leave it here for a second. There are multiple hypotheses to explain one phenomenon, which is the decline of a certain species, in this case stellar sea lions. And they can be explained via both top-down and bottom-up mechanisms. And being able to know what those top-down and bottom-up mechanisms may be important in being able to articulate, there's 4 bottom-up and 5 top-down, and kind of being familiar with those. Okay, that will wrap it up for this section 21.2. And holy smokes, yeah, we might have to do another 2. We'll see how it goes. There's not that much more in text, but it might end up being 2 more. We'll see. Okay.